remotely. I'm sorry I can't be there in person, but I'm happy to give an update on what we've been doing with the NEOWISE project recently, since our last SBAG update. So next slide, please. Just as an overview of what NEOWISE is for those who might not be familiar, NEOWISE is a PI-led mission led by Amy Meinzer here at JPL under PDCO to detect and characterize asteroids in the infrared. So using the two shortest wavelengths of the WISE spacecraft to complete surveys of the sky, to gather detections in the thermal infrared of all of the moving objects we see, so to do real-time searches for these objects, report those detections to the Minor Planet Center, and then use that thermal infrared information to determine diameters and albedos for the objects that we detect. Currently, we are operating at 75 Kelvin, passively cooled. We lost our cryogen at the end of the cryogenic mission back in 2010. And NEOWISE was reactivated in 2013, in December of that year, to start its new survey, and we are expected to continue through June of 2019 at the current plan, at least. And so, you know, the observations from NEOWISE represent a key component for future mission planning, both human and robotic, as well as planetary defense, because this offers a unique way of getting information about the size of the objects, and also in some cases for some near-Earth objects, the thermophysical properties of the surface as well for objects we have observed multiple times. Next slide. So to just discuss, to show you where these two wavelengths fall on a typical spectral energy distribution for an asteroid, on the left here, I'm showing a 1 kilometer near-Earth object, and on the right, a 10 kilometer inner main belt object for 4 different optical albedos. That's the PV number. And so you can see for the near-Earth objects, band 2, that darker blue bar, is thermally dominated in all cases. And so this is what allows us to set a constraint on the diameter, is by measuring the thermal emission and using a thermal model such as NEADM, we can set a constraint on what the diameter of these objects are. For near-Earth objects, band 1, the lighter blue bar, is often thermally dominated. And so this allows us better constraint on the beaming parameter in NEADM, or some more information on thermophysical properties for a full thermophysical model. In the main belt, it's a little more difficult. You can see that W1 tends to be reflected light for almost all albedos of main belt asteroid, and W2 sometimes can be a mix of emission or reflection, but for the darker main belt objects is entirely reflection. And so this is how we can still measure sizes for main belt asteroids using NEOWISE, even though we're not in our cryogenic phase anymore. Next slide, please. So some of our statistics. Since the start of the restarted operations, we have obtained over 900,000 infrared measurements of over 33,000 solar system objects, including nearly 1,000 different NEOs, 159 of which we have discovered as part of the survey, and 162 comets, of which 12 were discoveries by NEOWISE. Our most recent NEO was the PHA 2019 H7, which has a moderately high centricity of around 0.6 and a 200-meter size, with a VLBDO of around 2%. The largest recent discovery was back at the end of 2018. We got a PHA that has a size of 700 meters. And so we are regularly finding these very large PHAs that are being missed by other surveys, primarily because their albedos are very, very low, and so they're not reflecting a lot of the optical light. So this is really the power of the infrared, is to complete that missing gap in our sensitivity. So far, we have had 4 successful annual data releases. The release of the year 5 data is scheduled for March of 2019. And so IPAC down at Caltech is working on that data release, and this will be added into the other data that is currently available online. Next slide, please. This is just showing what our coverage of the sky looks like. This is a couple weeks old, but we're already over 10% of our way through our 11th coverage of the sky. So in addition to asteroid and comet detection, we are also making a time-sensitive map in the infrared of the entire sky. And up at the ecliptic poles, you can see there are some cases of objects with thousands of coverages, or in fact, the max coverage there is over 22,000 images, frames covering a specific spot on the sky at the north and south ecliptic poles. So there's quite a depth of data to be searched, and this is important, for example, for pre-covery. You can take an object that should have been detected by NEOWISE but might have been just below our detection threshold and do a later search for objects of interest. And so one of these objects was a PHA is a virtual impactor from a few years ago, 2017 XO, I think, or XO3. And so that one we were able to pre-cover in the NEOWISE data at the same time that the optical ground-based surveys were getting pre-covery data as well. Next slide, please. So here is a preliminary diagram of the diameters and albedos we've gotten for all the near-Earth objects detected in the first 5 years of the NEOWISE survey. In cyan, we're showing objects that were previously known, so had been discovered by a ground-based survey. In black, we're showing objects that were discovered by NEOWISE as part of our survey. And again, this is just to emphasize that we are discovering most of our discoveries tend to be dark in that lower cloud of the albedo axis, and also tend to be big. We're getting things that are hundreds of meters, in some cases a couple kilometers. So we're finding these last few objects that are above the 1 kilometer threshold, but previously were not known oftentimes because they have a high interest in a low albedo. Next slide, please. An example of one of the other interesting science tidbits to come out of NEOWISE. Recently, this is a paper that Rakutri submitted to the Minor Planet Bulletin, just discussing an object we covered, NEO 2002 WW17. NEOWISE was able to detect it 38 times in a single epoch and found a period determination of 10.5 hours from that and an amplitude of almost 2 magnitudes. So this is the highest amplitude object we have detected in our survey. And I believe it's comparable to, at least in terms of light curve amplitude and period, to Geographos. And so this is, again, being discussed in a recent Minor Planet Bulletin submission. But you can see the light curve maybe even has a hint of a possible flat bottom on one of those minima, which may indicate binarity or some sort of eclipse of one part by the other. So there's a lot of interesting data that we're being able to probe out of our data set. Next slide, please. As I mentioned, the data are public. The first 4 years are currently public. The 5th year will become public in the next few months. All of this is available at ursa.ipac.caltech.edu. And all of these databases are accessible online, both via GUI commands and also in a machine-friendly Ursa services. So there are ways to automatically query the database. You can query the catalog of detections and also the catalog of images, if you want images of objects as well. And there is a specific solar system object search. So you can type in the name of any solar system object, or in fact, a set of orbital elements if the object is not currently in the Horizons database, to search for possible detections of that object in our catalog. This was funded via part of the original NEOWISE program in 2009 to 11, and has been extended to the NEOWISE reactivation data as well. And these data sets are now being used for other services such as Spitzer and PTF are using these tools that Ursa developed, and they're implementing them for other databases as well. Next slide, please. Go back one. Yeah. So currently, there are over 1,000 refereed publications make use of NEOWISE data, NEOWISE discoveries, or NEOWISE-derived parameters. And that's out of around over 3,000 publications making use of the WISE data in some form or another. In addition to solar system work, a few recent papers using NEOWISE data for other uses have come out recently, including asteroid thermophysical modeling, again, pre-covery of potential impactors, variable stars. Lynn Hillenbrand had a few papers recently about stars that were detected exploding in Gaia and found pre-covery data of them starting to brighten in WISE a year or so before the optical detection. Recent papers on quasar variability, brown dwarf motion, and unusual exoplanets like Voyager star was covered. We caught the very beginning of one of the recent dips in that. And so the NEOWISE data was used for that analysis as well. And so this is just to highlight how important it is to have full frame data downlinked, because you can get so much more out of it than just individual detections, both in terms of pre-coveries and in terms of ancillary science. So next slide. Go back one, there we go. So in summary, NEOWISE is discovering and characterizing small bodies. Our diameters are accurate to around 20%, our albedos to 45%. I'm showing here a crop of one of the comparisons we did in our 2017 paper discussing the year 3 data release that just compared the diameters we measured in year 3 to the cryogenic diameters, and showing that on the far right there, the spread of that distribution was around 17%. And so this is, again, simply because we're on the Wien side of the spectral energy distribution, so the constraint is not as good as it was in the cryogenic mission when we were sensing the peak of the thermal emission. But we are still able to get diameters to 20% with the NEOWISE reactivation data alone. Orbital precession will eventually end our mission. We are still precessing away from our terminator following orbit. We're about 20 degrees off terminator at this point. On the evening side, the side precessing away from the sun, we can still point to zenith and we can still survey without too much issue. On the side precessing towards the sun, we're now having a case where we have to point 90 degrees from the sun because of our sunshade, but now we're starting to get more heat load from the Earth. And so at some point in the near future, either the heat load or scattered light from the Earth will likely force an end of the mission, but it's been difficult to predict how long that will be, partly because we don't precisely know when this heat load will cause an end of mission, but also because the precession has been much slower than we expected. The sun has been very quiet over the last 3 years, and that's meant that our rate of precession has just been much slower than we had pessimistically thought. So we will be able to survey at least until June of 2019, based on what we currently know about how the orbit is moving and the performance over the past couple of years. As I mentioned, we've observed over 33,000 small bodies since restart, and we're continuing to get more every day. So at this point, I'm happy to take any questions, and thank you for your attention.
Okay, questions for Joe? Any questions online?
Any plans to co-add the data?
Are there any plans to co-add the data?
So in terms of, so there is a group at JPL led by Peter Eisenhart that is co-adding the individual frames to do a deep stack atlas. We are also in the process of doing co-ads on the predicted positions of all moving objects. So in addition to things we can detect in single frames, you can also shift and stack on predicted positions. And so we're in the process of doing that for the data survey right now. Yes.
Okay, thank you. Other questions? All right, thank you, Joe. And so, let's see, we will go to